Okay, today we're going to continue looking at section 5. We just have a couple new little bits to add to it, but none of it's too bad. So, the idea that if I'm going to end up factoring a polynomial, the idea is you can actually have these different versions that we already talked about. You can have a rational factorization where you don't have any square roots in it. You can have a real factorization where it might have some irrational terms. It might have some square roots in it. Or you can have that linear factorization that takes it all the way down to x to the first power. Okay? So that's essentially what that's talking about. So if I have something like this, I want to find all the zeros of the function given that one zero. How many zeros does this function have? 3. Okay? One of them is complex. So you automatically know the other one's going to be is going to be a root as well, or a 0. Okay? And since those come in pairs, then I know the third one actually has to be real. But what I can do with this, if I know this 1 0 works for this, you can do synthetic division with this. It gets a little ugly. It's kind of like when we did the square root ones, where you'd have 1 plus the square root of 3, and then you had to do synthetic with that. Your other option is to take these two and get one of your factors. What I can do with this, I can take x minus these two things, because remember, it's x equals each of these. And x minus 1 minus the square root, 4i, or minus 4i, not square root. And if I FOIL that out, well, I'm going to get x squared minus x minus 4ix minus x, distribute the negative 1, plus 1 plus 4i, and distribute the 4i plus 4ix minus 4i minus 16i squared. Simplify that out a little bit. The 4ix's will cancel, and the 4i's will cancel. The negative 16i squared will turn into plus 16. So I have x squared minus x, or I'm sorry, minus 2x, don't miss that one. And then the 1 and the 16 gives you plus 17. So the idea is if I plugged in a quadratic formula to this, I would get back 1 plus 4i and 1 minus 4i. So using this now, this is a factor of this. So I can do long division on it now. So if you don't want to deal with the i's and have to FOIL all that stuff or multiply different sets of i's out, you don't have to. You can do it this way and then just do long division. So I have x squared minus 2x plus 17. Personally, I like the synthetic version better, but 6 of one, half a dozen the other. When I do that, that's going to give me x cubed minus 4x squared plus 21x minus 34. Then what? The nice thing is this will usually happen pretty quick because I'm only dividing x cubed by x squared. So what do I multiply by? X. So that's going to go here. Then multiply it. You get x cubed minus 2x squared plus 17x. Subtract everything there. So I do know this has to go in evenly, so I know my remainder is going to be what? Well, no, my remainder when I get to that point. 0. Yeah, negative 4 minus negative 2 will be negative 2x. 21 minus 17, 4x. I'm awake. Negative 34 just comes down. So what am I going to multiply that by now? Negative 2. So that gives me negative 2x squared plus 4x minus 34, which conveniently gives you a remainder of 0. So, if I want to find all the zeros of this function, this is what it asks. What are my zeros?
2.
X equals 2. What else? And 1 minus 4i. Like I said, if you like the synthetic version better, go ahead and do that. But you got to keep track of the i's all along there too. Questions on that one? Okay, let's do one where they give you a little less information. Write a function as a product of linear factors and list all its zeros. And all they do is give you the polynomial. Where would I start with this? Say again?
Find the zeros.
How? Can I factor it?
Yeah.
I could try doing it by grouping, but all I'm going to take out here is an x squared, and there's nothing in common between 41 and 51, so there's nothing that's going to come out. Is there any way I could find possible zeros?
Yeah.
How? What do you mean? Yeah. I can do P over Q. Right? Test for rational zeros. Those are the possible. Because 1 and 51 are factors of 51. Are there any others? Is there the amount of space I wrote probably? 17 and 3. That's the other ones. Tip, 5 plus 1 is 6. Since that adds up to a multiple of 3, you can divide by 3. Plus or minus on all those. Okay. So now, they're all over what? 1, so I don't really care. Let's see which ones work. How do I figure out which ones work and which don't? Yeah, plug it into the function. So in other words, do h of 1. If I do h of 1, I'm going to have 1 to the third minus 11 times 1 plus 41 times 1 minus 51. Well, if I add those up, will I get 0? No. If I make this negative, what's it going to do to these? All of them? Which ones?
Just the first one and the third one.
First and third, it's the odd powers. Yep. Anything that is an odd exponent here. That'll turn into negative 1 and negative 41. Well, considering everything there's negative, will that work? No. So let's try 3. If I plug in 3, that's 27 minus 99 plus 123, yep, minus 51. Well, let's see. I get 150 positive, right? What do I get negative? 150, guess what? 3 works. Now what can I do? Synthetic division. 3 in the upper left, and then your coefficients. So, now what? Drop the first one down. What goes beneath the negative 11? Down here? Up here? And nothing. So I end up with x squared minus 8x plus 17. What? Does that factor? No. So, now what? Yeah. Quadratic formula. Plug them in. Negative 8 negative 8 is just positive 8 plus or minus square root. Negative 8 squared is 64. Minus 4 times 17 times 1. 4 times 17 is going to be what? 40 plus 28. 68. All over 2 times 1. So what do I end up with under the radical? Negative 4. So 8 plus or minus square root of negative 4. What's the square root of negative 4? So 8 plus or minus 2i over 2. So I get 4 plus or minus i. So this thing has for write all the functions as write the function as a product of linear factors and list all the zeros. So what are my zeros?
4 plus I, 4 minus I, 3.
3. So literally those 3 things. So then if I want to write out the factors, the linear factorization, what will that look like? In the book, we'll usually put parentheses around here on the inside as well. I usually don't bother. Yes?
For the synthetic division, do you put in the p-values or do you put in the original equation?
Those are the coefficients from the original equation.
Okay, so you.
Yeah, because that's the thing you're dividing.
Yeah.
The p-values are just to get something that might work when you plug it in here for synthetic, when you make it in the upper left corner. Okay, one other thing. Rene Descartes. Have you heard of Cartesian coordinate planes? Right? Rene Descartes was the guy who, well, it's kind of a mess. Descartes and Fermat actually, Descartes wanted it so instead of just an XY axis, you could, by being 90 degrees, you could actually have them meet at a slant or any other angle you wanted. His math actually worked off of that. Fermat was the one who had it solid, but we still name it for Descartes, basically because he did the coordinate system where you have XY. So it gets really messy. And then one of them wanted vowels to be variables, so instead of using X, Y, Z for all the variables, he wanted to use A, E, I, O, U. But, and the other guy wanted to, so it was Fermat wanted, I think, X, Y, Z, and then A, B, C for constants, and then X, Y, Z for variables. Descartes was the one that wanted A, E, I, O, U, vowels for variables, and consonants for constants. But I think they actually got to the point of challenging each other to a duel at one point over it. It was a weird time. Anybody know what Descartes' most famous for, though?
Having a funny name.
You ever hear the phrase, I think, therefore I am?
No.
Yeah.
Yeah, that was him. He was a philosopher as well as a mathematician. Anyway, he also came up with something called the rule of signs.
I feel like that's a pretty bad mix.
Actually, a lot of them are. Scary amount are back previous to like 1700s. Look at any long polynomial. Descartes figured out a pattern. Okay? If you look at the way that the signs vary in the polynomial, so if they switch from positive to negative or negative to positive, the number of times that happens will actually tell you the possible number of positive integers you have as zeros. It'll also, if you make it f of negative x instead, so if you were to plug in the opposite, however many variations you have there will tell you the number of negative integer solutions you have. Or negative real solutions I should have, not integer, sorry. But it'll always be that integer number, just a real solution. So the idea is you're looking at every two consecutive coefficients. If they have opposite signs, that's considered a variation. It's really weird when you first read it, but in practice it's not too hard. You just look at the polynomial. Okay? And I see that this first one's negative, the next one's positive, right? So I'm going to mark that off. It goes from negative to positive. Then it goes from positive to negative. Then it goes from negative to positive, right? So if I look at this, how many variations are there?
3.
So there are 3 variations in f of x. Variations of sign. Okay? So that means 3 or 1, I should say, positive real zeros. So it either has 1 real zero or 3 real zeros. Okay? Now, if I look at f of negative x, well, what's that going to do to this polynomial? Flip what? Then flip what? The odd powers. Remember, 5x squared will not change if you do 5 of negative x squared. So it'll flip the 2x cubed over. It'll leave the 5x squared alone. It'll flip the x and leave the 8 alone. So how many variations do I have here? 0. Since there are no variations, then there are no negative real zeros. So what that means graphically, if I was looking at it from this perspective, that means there are no x-intercepts to the left of the y-axis. Either you're going to have one time it's going through here, so it'll look something like that. Well, actually, then I made it hit. Let's call that 3 times there. So either it's going to have those 3, or it'll just look something like that. That's what that's saying, because this is to the 3rd power. And since it's negative, how should I have started it? Yeah, I should have started up on the left, coming down. So actually it would be more like that, or like that. That's all that's saying. So if I go back and look at one of the previous ones, well, again, I have one variation, two variations, three variations, right? And if I flip the signs for f of negative x, this will become negative, this will become negative. Again, all those are negative, right? So by Descartes' rule, either one or three of your solutions are positive reals. How many positive reals? One. Do the same thing down here. Again, you have one, two, that's the same type of problem. You have 1, 2, 3 real solutions, or variations, I should say. And if you flip these two, you end up with none. Okay? So take a look at, so one way you can tell quickly that if you had these rationals to choose from, just based on Descartes' rule, what could I throw out? All the negatives. Because I know none of the negatives work based on Descartes' rule. Questions? Yes?
Okay, so like to be a variation, does they have to be like next to each other?
Yes, they have to be consecutive.
Okay.
So as you're going along. So if I had something that was, let's write one out that's hideous. So if I had something that was like x to the fifth plus 4x to the fourth minus 3x to the third plus 2x plus 1. I don't have any variations until I get to here. Okay? Then I have another variation, that's it. There's only two variations in that one. That's what that's talking about. Questions? Okay. Rest of the time is yours.